Okay, so for type 2, we're going to look at a lamina or flat plate that has uniform density rho, and our goal is to find its center of mass, called the centroid. So basically we have a flat plate as such, and we want to kind of think of where would we place the fulcrum to find its center of mass so the thing balances on it, and it has uniform density rho. One fact you want to keep in mind is that the mass of this plate is simply the density, the uniform density times the area. So since it's a flat plate, you can just say, instead of normally we say density times volume to get the mass of a three-dimensional object, this is just going to be density times the area of that lamina. Also recall from the discrete case that we derived that x bar is the sum of the moments over the sum of the mass of the system, and y bar was sum of the moments over the sum of the mass of the system. Now we're looking actually at a continuous case where there aren't point masses, but rather a flat region denoted by possibly a function f of x. So our goal right now is to find the centroid of a lamina, a flat plate, bounded by some function f of x. So here's my lamina or flat plate, and it's bounded by the function f of x. So the rough idea, again, we're going to chop up our interval into from a to b into n subintervals, and we're going to focus on one piece and then add up all the little pieces and find the center of mass of the lamina. So if I come and chop it up and just focus and zoom in on the ith interval, on the ith piece, you'll notice that I have roughly a rectangle. And if I'm looking at a rectangle, I kind of already know that the center of mass will have to be right smack in the middle. But I'm going to go develop x bar and y bar by looking at this piece. So one thing I need is the mass of the whole system, in other words, the mass of this big chunk that's bounded by f of x to use for my x bar and y bar. Then we'll have to go look at my moments, mi x I and mi y sub I as well. So let's focus on the mass of the system for right now to be able to put them into those places. If I'm thinking of the mass of the whole system, remember this is a plate with uniform density, so mass will be basically rho a. So what I need is the uniform density times the area of this chunk. Well, the area of the whole thing I already know is just the integral from a to b of f of x, because that's area under the curve, and this curve, the area under it, creates my lamina. So mass is simply a to b rho f of x dx. This will give me the area under the curve times the uniform density will give me the mass of the whole system. I could look at it piece by piece, or just know that that's the area of my entire, of the curve, under the curve of my function. So we've got the mass of the whole system using the integral, so this piece is done with. I have that part. Now let's go focus on the moments. So now let's say I want to find the moment in y, so my, m sub I, x sub I, I'm looking at the sum of this. I'm looking at one piece, but of course I'm going to add them all up. In analyzing this, we know that our mass of that one piece is the uniform density times the area of that one piece only. I'm only focusing on that one piece, times xi. So in finding the area of that one piece, well, the area of that one piece is really the area of this red piece that I'm focusing on. So area of that one piece is simply its length times its width, and then my x sub I as well. So if I'm focusing on the area of this one piece, well, its length is basically given by the height of the function. This will be f of, let's say, x sub I. So that's our length of that piece. And then the width is this little distance, delta x. And xi this piece is simply because I'm at the ith location. How far is that from the y-axis? That's x sub I. So the moments end up being, well, the sum of rho f of xi, delta x, and this distance xi, that you can think of it as a point mass focus there because I'm just dealing with a rectangle. So that's xi, and as I let n to go to infinity, we're going to end up with a to b, the integral from a to b. We got our rho, we got our f of x, we got our x and our delta x, which will be our dx. So far, I've got a representation for my moment in y, and I've got a representation for my mass of the system. Remember, this is really just mass of the entire system. I'm calling it m and not introducing the m sub I business, because we already know what the area under that curve is. So I got this piece, I got this piece. I can already figure out the x-coordinate of the center of mass. But let's go analyze the next piece as well. So now I'm looking at the sum of mi yi to see what I can figure out from my picture here. So again, I got the sum of my mass of that one piece in the ith location is the uniform density times the area of that one piece, which I already know from before. And I still have the y sub I going on. So nothing has changed so far from what I did above. So I have rho. Let's do our length times width of the red rectangle like we did here. We have it right there. Length is f of xi, width is delta x. And so I took care of this, and now I have to worry about y sub I. Now notice y sub I is from here to here, and if I want to put it in terms of x, well, since we talked about this is a symmetric region, a rectangle whose center of mass should be right smack in the middle, we know that that right there is really f of x sub I over 2. So basically yi is halfway between here and here, so it must be f sub xi over 2. I can think of this as a point mass concentrated right there, so that point mass is half of f of x sub I away from the axis, which it has a tendency to rotate about. So my yi right here is really just f of x sub I over 2. So I took care of that as well. Now as n goes to infinity and I add up these little pieces, we end up getting from a to b, we've got our uniform density, we've got our delta x, and then this guy and this guy give me f of x quantity squared over 2. So now we have the second piece that we needed as well. We got the moment in y, sum of mixi for this continuous region, and we got the moment in x, sum of miyi, and we already know what the mass of the entire region is as an integral. So let's go put those together and look at what the continuous case will be like we did for the discrete case earlier. So the first piece, the moment in y, we found right here. Let's go put that in. We've got integral from a to b. Let's put the rho outside since it's a constant anyway. And we'll put x, f of x, dx. And then in the bottom, we have the mass of the whole thing, which right here is an integral, the function times the uniform density. Let's pull out the uniform density, a to b, f of x, dx. Now notice what happens. It makes sense that the uniform density is going to cancel out, because if it's uniform throughout the whole lamina, then the center of mass will work itself out accordingly, since the density is the same all around. And our y bar accordingly will be rho, a to b, this guy right here, I pulled the rho outside, f of x quantity squared over 2 dx all over the mass a to b f of x dx. And similarly, you'll see that the density goes away. So we have now the x-coordinate and the y-coordinate of balancing that lamina. I'm going to call this just A because that's simply the area under the curve you're dealing with, so that we don't have too many integrals flying around. We can just do them separately when we do the computation part of it. So we finally arrive for the continuous case. X bar is just going to be 1 over the area of whatever your curve you're looking at, times the integral of f of x times x dx, and y sub bar will be 1 over the area of whatever region it is that you're looking at, from a to b a half f of x squared dx. And these are the two pieces that will give you the center of mass of the region. And once you find them, since there's a lot of calculations going on, you should look at your region to make sure it kind of makes sense that the center of mass would actually lie there. One little note that might save us some time on the computation is if a lamina or flat plate has a line of symmetry, then the centroid will have to lie on that line. What do I mean by that? Let's say I'm looking at this region, and I want the lamina looks like this, and I want its center of mass. Well, x sub bar, I shouldn't really have to go calculate x sub bar because there's a line of symmetry right smack in the middle. So it seems like x sub bar should be 0 in this case. It has to lie on that line of symmetry. Y sub bar I have to go find. And when I do go and find it, this shape seems sort of bottom heavy if you look at it. So I'm guessing that the centroid will not be up there or in the middle, maybe more towards the bottom because it seems a little bit bottom heavy compared to the top. So this might save you some work. If it's symmetric about a line, you can reduce the calculation in finding the centroid. Let's look at an example. Find the location of the centroid for this curve bounded by y equals 0, x equals 1, and x equals 2. So before we do anything, we're going to draw a little shape or sketch it to get an idea of the centroid that we find, whether it kind of makes sense or not. So I'm looking at y equals 1 over x. I have a branch here, I have a branch here, but I don't care about the bottom branch because I'm bounded by, it looks like y equals 0, x equals 1, and x equals 2. So all, and above, of course, by the curve. So bounded above, below, right, left, this is the guy I am focusing on. So just visually looking at this region, it seems to be a bit bottom heavy. By that I mean you have more stuff, more of the lamina in the bottom than the top, because the top, the right part is sort of shaved, the top part is shaved off. It's also kind of left heavy because the right side contains less material than the left side. So if I had to guess, I would say the centroid is maybe somewhere around here. It can't be here or here or here or at this corner. Maybe somewhere here, roughly speaking, might be the centroid, because again, it's sort of bottom heavy and left heavy. But let's go ahead and compute using these two ideas, which is really just being able to do integrals. So I'm going to find A first, which is just the area under the curve, and that's going to give us ln of x from 1 to 2, which will be ln of 2 basically, because ln of 1 is 0. So we have our A value. Then we're going to find the ln the integral of x f of x dx and the integral of a half f of x squared dx, and use it with this to find the centroid. So that's just going to give me the integral of 1 dx. So you can pause the video here to see what happened. I found the integral of 1 dx, put in the limits, we got a 1, and I found the integral of f of x squared times a half, and integrated, and I got 1/4. So x bar is 1 over the area, which I found from before, and y bar is 1/4 over the area, which I found from before. And approximating them gives us a visual of what we had our intuition be was correct. It's left heavy, bottom